Hello all, thank you for joining me today. My name is Karina Puente and I am a rising senior in the Mechanical Engineering Department at Texas Tech University. Today I will be presenting optimizing a hexapod robot using heuristic genetic algorithms. So, have you ever wondered what happens after natural disasters such as hurricanes, tornadoes, earthquakes, and so on? Well, I started this project with that in mind. After Hurricane Harvey struck in my hometown, Houston, Texas, I wanted to stop sitting on the sidelines and do something about it. The best thing I could think of was making a search and rescue robot. But since I didn't have the knowledge to do that, I decided to start this project with the hope that I can learn from it so I can one day create a search and rescue robot to locate people lost in the debris. So I like to move on to the outline here, and we're going to go through the intro, the methodology, the research questions, literature review, hardware, servo motors, and so on. So let's get started. So for my intro here, since my goal is to create a search and rescue robot, I have decided to expand my knowledge in researching optimizing techniques for hexapod robots. So, robotics has always been a passion of mine, so this project was actually really fun to do. Additionally, I will also be presenting on a new topic that I'm currently researching, which is gates. So, for the methodology of a walking robot, you would have to define the problem, research and design it, create a prototype, build the robot, program and test the robot, and lastly, evaluate the robot. So for defining the problem, that is essentially my research questions. Researching and designing would be the literature review, while creating a prototype would be testing out the microcontroller, servo motors, taking voltage readings, and so on. For this, I had to familiarize myself with Arduino components and more sensors. For building the robot, I had to define the type of hardware components I used. So I'm going to be presenting that later on in these slides. Then I have programming and testing the robot, which is actually me creating the code using Arduino IDE free programming software. I then tested the robot by implementing a small version of an HG algorithm. I will speak more about HG algorithms in the literature review. And then lastly, evaluating the robot would be me conducting a several time trials where I took measurements how long it took a robot, my hexapod robot, to complete the 3 feet from start to end. So here are the research questions. To what extent can a hexapod robot be optimized to walk before implementing heuristic genetic algorithms? And does adding an HG to the code improve the speed of a hexapod robot? So for question one, in this case, I will be presenting a small approach to adding an HG algorithm, and I will also speak about the concept that I am looking into, which are gates. So here I have heuristic genetic algorithms. And I would like to point out this small little graph here, or image, which shows what an HG algorithm is. Oop. So HG algorithms, this is a type of algorithm that reflects the process of natural selection where the fittest individuals are selected for reproduction in order to produce offspring to the next generation. In this case, the offspring would be the pieces of code taken within the code to create a more efficient one. So for here, you would see that you can generate the initial population, decode and evaluate the initial chromosomes, generate the offspring, and so on. Decode, evaluate the offspring, select the chromosomes for the next generation. From there, you can either choose to terminate to find the best solution or just go back until you keep finding the best solution available. And so the focus point I like to point out here is that HA algorithms minimize the time required for robots to complete transportation and manufacturing tasks using generic algorithms. So now I'd like to talk to you about gates. So what are gates? So gates are leg pattern movements. Gates have the capability to increase the order of speed from walking to running. So for this, I want you to think of a horse galloping, okay? A horse has four basic gaits, which are walking, trotting, galloping, and pacing. So I have provided a small visual element here in this slide for you to actually imagine that. So I'm first going to go through what each one is, and then I will play the animation. So for walking, when walking, a horse's legs follow this sequence, which is left hind leg, left front leg, right hind leg, right front leg, and a regular 1, 2, 3, 4 beat. For trotting, in this case, the horse moves its leg in unison and diagonal pairs. For galloping, it is the fastest pace or the fastest gait also for the horse. It strikes off with its non-leading hind foot. The second and third stages, because the inside hind foot hits the ground a split second before the outside front foot hits it. Then both gaits end up with a striking off to the leading leg, followed by a moment of suspension when all 4 feet are off the ground. And pacing would just very regularly. Imagine just walking around. It's a little bit faster than walking, can be a little bit slower than walking. It really just depends on the horse there. And it's the same thing with gaits. So why is this important? Well, gaits have many mutations, making it possible to apply random HE algorithms in the sequence to get the robot to have the fastest speed. So now you can see, I will click in and you will see the small animation and you'll see how the walking is. It's just as I described it before, and it's just slow down a little bit. Then we have the trotting, which is diagonal, as I said before. Then we have the galloping. And lastly, the pacing. So knowing that, now we can move on to the literature review for my gaits. So this is the literature review I've chosen for the gates, and I thought this was an amazing article because it does a great job in explaining the steps necessary for creating gates. And here in the image to the center, you can see that the main steps to create gates are to one, create a model of the system, analyze it. Second, conduct modulations, which are just sampling different gates to get to the fastest pattern and learn about the gate transitions. And lastly, is actually the fun part, which is just applying the previous steps and seeing how it functions. Now, please take note of the images to the right. These are movement patterns. The black bars correspond to the gait patterns reported and it is used for moving the femurs, while the gray bars are added as additional information for moving the coccyx and thus achieving the full locomotion in the hexapod individuals. And I don't know if I mentioned this before, but just making sure, the CPG is again the central pattern generators. And also the image to the left is just a robot or their type of hexapod robot that they use for this experimentation. Lastly, I would like to present animal locomotion, which is also another type of literature review that really helped me create my project. So this was an introductory into animal locomotion since the design mimicked a snake-like body of movement for this research. The researchers took a different aspect of the snake's body to create this robot. So this device also comes with an external device where people can use to locate the snake and the snake-like robot while it is in the debris. Now I'm going to move on to the hardware components that I used. And here I have the Arduino Uno microcontroller, which is essentially the brains of the operation and where the code gets uploaded to. Then we have the servo motors and legs. So a leg is composed of 2 servo motors, one horizontal and one vertical. Then we have the robot chassis, which is all the legs added to it. And it kind of looks like a spider, if you can see. And lastly, we have second to lastly, we have the breadboard. The breadboard has all the connections there, and it also has the power supply and everything. So I also like to point out these servo motor wires, which are attached to the servo motor, of course. The orange indicates a digital input that is plugged into the Arduino Uno microcontroller, while the red is the power, and in this case, I will be using 5 volts. Anything more like such as 7 volts or 12 volts would fry the Arduino Uno microcontroller. And we don't want that. And of course, lastly would be brown is the ground. And that's also in the blue area of the breadboard. That's how I set it up. So now I'm going to show you how I tested the servo motors just to see if they functioned. And that's in the first image or video, actually. You can see that it works. It's able to go from like around 0 to 90, 95 degrees. And that's exactly what I wanted. And in the second video, you can see how these 2 legs are actually moving in unison. And that's also a great thing because that's what we want to do here in this project. Now I have the complete walking robot. I would like to note that I did see that there was a lot of wires and everything, and I did take them away after recording this. So Here's it, just moving. So this is the code I used. I would like for you to please pay attention to lines 45 and lines 55. So that is what I am changing. This is what I'm changing. So by me changing this, this is me actually applying a small HU algorithm because as you know, they have to be random. So I just wanted to apply a small one. And later on, the next slide actually will present all the trials that I ran and how it affected that. Also, in theory, once I apply gate sequences to the code, I can create a more realistic HU algorithm code because I will be able to implement a randomization factor into it. As it is now, as I said before, it's just a small version of an HU algorithm that delays the speeds of the servo motors. And here we have the trials that I ran. And as you can see, I have a constant of the horizontal delays for the first pattern of 10 seconds. And then I also did it again. I ran 5 more trials for the vertical delays and maintained it at 10 seconds. But as you can see right away, just by adding a small HG algorithm, there's a significant difference. And here are the graphs of the tables I just presented. There are some discrepancies here because the servo motors do not have enough power to support the chassis. As you can all see, the best approach is to change the vertical delay time because the time is actually faster there. That being said, there are some benefits in having horizontal delays because the reach is farther and more distance can be covered. So I'd like to conclude with this. So for my questions before were, to what extent can the Hexapod robot be optimized to walk before an HE algorithm is implemented? And my answer would be, the extent at which the Hexapod robot can be optimized correlates with the original code without inputting the delay times. And does adding an HE to the code improve the speed of a Hexapod robot? Well, the answer is just by having and running 5 trials of each servo leg, it is apparent that adding some form of HE algorithm to the code has increased its speed. And so here is my future work. Step 1 would be to determine 2 to 3 gate patterns for the leg movement. Secondly, I'd like to determine the best gate pattern and mutate it. Third would be to apply the gate pattern to the source code. And lastly would be to compare the results from the original code with small HU algorithms. So that is basically, for step 4, I would want to use the code that I had used for this original project, and then I would apply the gate patterns, which would make more HG algorithms in essence. And so here are the references I used for today's slides and for the literature review as well. A big thank you to my mentor, Dr. Aksak, and the McNair Scholars Program. Without them, this would not have been possible. Thank you very much, and I hope you enjoyed watching this presentation.